Okay. So moreover, using the property of integral, we can also discuss the property of volume. The volume we defined here enjoys the usual natural property. For example, if D1 and D2 are Roland domain, then their intersection and their union are also Roland domain. Therefore, they have a union volume. Okay, they have a union volume. So how about the relation of the volume? We have the following result: D1 union D2. The volume of D1 union D2 is the integral of D1, the constant function over this union. But using our previous theorem, we know that this equal the integral over D1 plus the integral over D2 minus the integral over the intersection. So these three integrals are precisely the volume of D1 plus the volume of D2 minus the volume of D1 intersect with D2. Okay, so this is the quite natural and reasonable result. Okay, so we draw a picture to illustrate this result. So this is D1, and this blue one is D2. Their intersection is the red reason. Okay, so the total volume of the interunion is the sum of both D1 and D2. Volume of D1 and D2 subtract the volume of the intersection. So this is quite natural result. Okay, so we have developed a very good understanding of integral. Okay, but how to compute integral? We have not discussed the computation of integral. Although you have studied calculus 2, at that course you studied last year, you should know how to compute the integral. But maybe the method, the main theorem introduced in that course have not proved. Now we will prove those theorem and also generalize to more general case. For example, higher dimensional case. And also I will show you some clever example. Okay. So our first method, the integral multiple integral is a higher dimensional problem. The method to deal with such a problem is to reduce the dimension. Lower dimensional case is easy. The one-dimensional integral is precisely the integral we studied in the single variable calculus. We know how to compute such a definite integral. Okay, but for integrating multi-variable functions, this is the idea is to reduce the dimension, transform the problem into the computation of a single variable integral. Okay, so this is the Fubini theorem. So we will talk about Fubini theorem. So to study the Fubini theorem, this is Rm, and this is Rn. So we take a rectangle in Rm and another rectangle in Rn. So this is A and this is B. So their Cartesian product. What's this? Their Cartesian product A cross B. Maybe I will write in red. Their Cartesian product is a higher dimensional rectangle. The dimension is the sum of m and n. Okay, so A is rectangle in Rm, B is rectangle in Rn, then the Cartesian product is rectangle in Rn plus n in a higher dimensional space. Okay, so suppose we have a function defined on the Cartesian product. Suppose we have function f defined A cross B, real value, the bounded function. So it is quite reasonable to expect such a result. The integral of f over the higher dimensional rectangle should equal, we integral which the second variable first. Okay, then we integral over the first variable, and we wanted this result to be true. This is an iterate integral. The inner integral is with respect to the last n variables y. Okay, so but the value of this inside the integral depends on x. So the integral give us a function of x. The value of x is the integral with respect to y, because this integral depends on x. For every x belongs to a, this integral makes sense and belongs to and depends on x. Therefore, this defines a function. This defines a function on a. So we can integrate this function over a. Okay, so this is an iterate integral. So to simplify notation, such integral is often written by this way. Okay, for we want this result to be true. If f is integrable over a cross b, we want this result to be true. This integral equality to be true. But there is a question: if f is integrable over the Cartesian product for x in a, the function we defined as a function of y might not integral over b. Can this be true? Can the integrability of f over the Cartesian product implies that fixed x considered f as a function of y, so such function is defined on b? Can this function of y integrable on b? This is an interesting question. The answer is no. It is easy to give examples where multi-integral, double integral make sense, but the inside integral make no sense. Okay, so I give you a chance to construct such example. Okay, anyway, the answer to this question is not true. Okay, it's no. Therefore, if this function is not integrable, so you could not write in the integral, inside integral. Okay, so what should we do? So we will solve this problem. A theorem. Suppose A and B are rectangle in Rn and Rn respectively, and f is integrable over the Cartesian product. Then the following function. Denoted by I plus minus as a function of A on A. The value of such function at x is this. But this integral might not exist, as we said before. But I don't care whether this integral makes sense. The upper integral and the lower integral always make sense. So we consider the upper and the lower integral. It always makes sense. Only when the upper integral and the lower integral coincide, the function is integrable. But even if the function is not integrable, upper integral and the lower integral always make sense. Therefore, this function I plus and I minus are always make sense. Once f is integrable, even if f is only a bounded function, even if f is not integrable over the Cartesian product A cross B, these functions I plus and I minus still make sense. For any bounded function, you can compute the upper integral and the lower integral. Okay, so these two functions make sense. But the conclusion of this theorem is that if f is integrable, then these two functions, I plus and I minus, is integrable over A. So a little surprising, is integrable over A. And we have the following very wonderful result. The integral of f over A and B equals the integral of I plus and I minus over A. And this integral we denote by the last equality is just a notation. Okay, as we see before, to save ink, we want to write the iterated integral in the last form. Okay, so that is the last form here. This is nothing but another way to write the expression here. Okay, so this is a very important theorem and very useful, and the proof is not difficult. Okay, so let's prove this theorem.